Hello everyone, welcome to the numerical methods class. In this class we will be talking about optimization, and we call this as chapter 8 because we continue after chapter 7 to chapter 8 in this class. But in your book this optimization part is given in chapter 13. So if you want to follow in your book, you can go to chapter 13 to read about optimization. Optimization is actually similar to root finding. The difference is that in the root finding, we are finding the roots which actually crosses the zero of x-axis actually, or the function is zero. But in the optimization, as a difference, we are finding the maximum and minimum values of the curve. So as a similarity, we are finding some values on the curve, but instead of finding the roots which gives the zero function value, we find the maximum and minimum points, or the x values which gives the minimum or maximum of the fx in the optimization. And the optimum is actually called as the point where the curve is flat. Basically, here this is the optimum point, or this is the optimum point, we can say. If the derivative is smaller than 0, the second derivative, then the point is maximum. If the second derivative is greater than 0, then the point is minimum. And the flat means here the first derivative is 0. So we will be focusing on the first derivative. Whenever it becomes 0, that means it gives us a maximum or a minimum. But the second derivative gives the information about maximum and minimum. If it is smaller than 0, the second derivative, it's maximum. Greater than 0, then it's minimum. And a strategy to find the optimum point is that finding an optima by solving the root problem for the derivative equals 0. So in the root finding, if you remember, we were actually solving for fx is 0. In the optimization, we are solving the f prime x, the derivative is equivalent to 0. So we take the derivative of the function, then we use a root finding to get the 0 function value, so that we can get the optimum points, which are the minimum or maximum points. However, the problem is that the derivative is not always available analytically. In such cases, we need to use finite difference approximations to estimate the derivative. So basically, similar ideas that we used in the root finding can be used, but those will be used for the derivative instead of the actual function. In this slide, we will check a little bit more about the mathematical background of the optimization. And optimization is also considered as a mathematical programming because we are using actually programs, and it's basically based on mathematics. And this can be generally stated as a formulation like this. We want to find an x, which is a variable, we can say, to find, to minimize or maximize the function value. So we want to optimize this as a minimization or maximization of that. And we can have some constraints. Those are identified like subject to. This is a constraint as inequality, and this is a constraint as the equality. So we have this objective function, the variables we want to find, or a vector of the variables, and a and b are the constants in the inequality and equality constraints, and we define these as the constraint thresholds or limits, let's say. So we have m and p values here, which are the number of the constraints. If those are 0, then there is no constraint. That means we will have only minimization or maximization problem. This is called unconstrained optimization. Also, we can have p plus m smaller than n. In this case, we have constraint optimization. N is the number of variables, here n-dimensional design vector, and if the constraints, the summation of the constraints are smaller than that, then we will have a constraint optimization. But if it is greater than that, then we will have over constraint. So we will have more than expected constraints. So this is not wanted because this will constrain too much that maybe we will not be able to get any results. So these two are usually the classification of the optimization: an unconstrained without any constraints, and a constrained optimization. And optimization problems can be classified on the basis of the form of fx. And fx and the constraints are linear. If this is the case, we have a linear programming. So the function can be linear and the constraints as well, because these are functions too. Then we will call it a linear optimization or linear programming. If fx is quadratic and the constraints are linear, then we will have quadratic programming. And if fx is not linear or quadratic, and or the constraints are also non-linear, we have nonlinear programming. So linear, quadratic, and nonlinear programming, depending on the types of linearity or nonlinearity of the fx, the objective, and the constraints. In this slide, we will talk about the dimension of an optimization problem. It is actually the number of variables. So if we have one-dimensional problem, that means we have only one variable in the optimization, and it's called also single variable optimization. And we have a function which has only one single dependent variable. Here you can see fx function has only x, which is one single variable. And the search consists of climbing or descending 1D or one-dimensional peaks and valleys. You can see here it's just going down or up on a one-dimensional curve, you can think. Not one-dimensional curve, but two-dimensional curve, but the movement is in only one path, we can say. And minimizing fx and maximizing minus fx will be the same. So if we want to minimize fx, that means we can have the minus fx as the opposite of the curve, which is like mirrored version, let's say. In that scenario, here we want to find minimum, here we want to find maximum. It's the same if we have the mirror of the function, basically minus fx. They will both lead to the same value of optimized x. This x star is optimized x here. And we will have also multi-dimensional problem, which doesn't have only one variable but more than one variable. This is also called multi-variable optimization. In this scenario, for example, when we have a two-variable optimization, we will have an x variable and y variable in the function, you can see here. And in this scenario, we will have a in the two-dimensional scenario, we will have searching of peaks and valleys not in a single direction but in two directions. So and that's why we will have a topography or some contour bars, as you can see, which represents the function, and the increase or let's say decreased dimensions of these shows an optimum point, a minimum or maximum. We can come here in a 2D path, let's say. Instead of going over one line only, we are going on the surface in the 2D. And in 3D or more dimensional problems with more variables, the demonstration with plotting may be difficult. That's why we are showing only with 2D or two variables here. But the idea is this way. The function can have different options to reach to optimum point while moving from one point to the optimum in the multidimensional case. Firstly, we will be talking about the one-dimensional unconstrained optimization without any constraints. And in 1D scenario, actually in other scenarios as well, but in the 1D we can show it easier, both local and global optima can occur, and such cases are called multimodal. So if we have like maximums and also minimums, both local and global, then we will have a multimodal function, let's say. So what is the difference of local and global? Actually, global is the highest maximum, because there can be other maximums or other minimums as well. But the highest of the peaks will be the global. Similarly, at the bottom, it's the minimum, global minimum. The ones which are smaller than these highest ones will be called local. These are important as well because the optimization algorithm can reach to the local while going from the path of the curve instead of reaching to the global, and that may not be the actual final result. So we have to be careful about the local maximum and minimums. And in the optimization, we want to find the absolute highest or lowest value of the function, which means the globals. So we must take care that we don't have a mistake of finding a local result instead of a global one. And distinguishing or differentiating from the global from local extremum can be very difficult. And there are usually 3 ways to approach this problem. Let's check them here. If we have a low-dimensional optimization problem, then a graphical investigation will help. You can see here, we can easily see that, okay, the global is somewhere between these values. And we can start closer to this and go to this optimum global value. But if we don't plot a graph, then we may start from here, for instance, and it can go to the local value. And that can be a problem. So graphical investigation is a good solution and recommended if it is possible. And we can generate starting guesses randomly with large variations. So we can, if we are not able to check the graphical investigation, maybe we have a more than 2-dimensional optimization. In that scenario, we can start with different points here, 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 and we can see which one gives the highest minimum or highest maximum. It will provide us the global maximum eventually. So for each guess, we obtain the optimum point, select the largest or the smallest for the minimum as global. Another option is to perturb the starting point associated with the local optimum and see if the routine returns a better point or always returns to the same point. So let's say we found this point, then we are going to perturb this as a second initial guess. So we will start the optimization again, for example, from here or here. So we will perturb the value a little bit. Then we will see if it goes to this here again or goes to another value. Maybe it goes to here and finds another maximum which is higher than this. Then we will say, okay, actually this is a local maximum. So these are the 3 options that we can use to have to find the maximum or minimum as the global ones. In this class, first we will start with the optimization methods for the one-dimensional optimization problems. And these are actually similar to the root finding methods. That's why their names are similar as well, bracketing methods and the open methods, as you can see here. And you know, the optimization methods are actually very related to the derivative of the function, because if the derivative of the function is 0, then we can find the optimum point. And those kind of methods are called the gradient-based methods, derivative-based, in other words, methods. And these are open methods in the root finding process, which are the gradient descent and also Newton's method that we saw in the root finding as well. Basically, we find the root of the derivative of the function. But we can still use the methods without derivative. So we call it non-derivative or non-gradient based methods. And those are similar to the bracketing methods in the root finding. That's why it's called again bracketing methods. The first one is the golden section search. And initial guesses are made that bracket a single optimum. And a golden section algorithm is used to be able to continue in the iterations. There is also parabolic interpolation. This can converge faster than golden section, but sometimes can diverge. And there is also Brandt's method, which is a combination of golden search and parabolic interpolation. And let's see these two in an order, starting with the bracketing methods first in the following slides.